Alright, so for this video we're going to be taking derivatives of logarithm functions. Specifically, we're going to start off with natural log. So if you have y as a natural log of x, okay, there's a couple ways to do this. Now, my first and favorite way to do it is this. I know what the natural log function looks like. It looks like this. It's got a really steep here as you head towards 0. Positive slope though. Really positive. Very steep positive slope. And then it peters off and has a slope approaching 0 as it gets out here. Well, I happen to know a function that works for that. A function that describes that sure looks like this. Oops, well, it comes down, doesn't hit the axis. It looks like that. And it turns out that this function is 1 over x. And so it turns out that it is true that the derivative of the natural log of x is 1 over x. Okay? That's one way to do it. Another way to do it is to turn that inside out and write e to the y is equal to x, right? Because they are inverse functions of one another. So that's a true statement, just like when we did the arctangent one. Now, what's the derivative of e to the y? Well, it is e to the y dy dx is equal to what? Well, it's equal to 1. So dy dx is equal to 1 over e to the y. But what is y? Well, remember, up here somewhere we had y was equal to the ln of x, right? Because that's what we're trying to take the derivative of. Well, this is not wrong, but you need to resubstitute it back in. And what is e to the ln of x? Why, it's 1 over x. Okay, so that is the function that we're talking about. Now, this function, that's true, but remember that ln of x is only defined when x is bigger than 0. So we're only talking about the part of x, 1 over x, that's bigger than 0. That's kind of a big deal. Will be a bigger deal later when we get to Calc 2, at some point when you take Calc 2. That'll be a bigger deal, but it will come back to us again. Well, now, what if you have the ln of just any power, the log of any base of x. Again, let's just set that baby equal to y. Well, once again, that is the same thing as saying b to the y is equal to x, right? Interesting. So the derivative of x, of course, is 1. What's the derivative of b to the y? That's weird. Well, it turns out that the derivative of b to the y b to the y is equal to b to the y times the ln of b. B to the y times the ln of b. Well, that's cool. And so, if you want to dy dx. So if a person wanted to solve for this, they'd divide over here and they get 1 over the ln of b times, I'm going to write it like this, 1 over b to the y is equal to dy dx. Now remember, 1 over ln of b is great, that's fine, but then 1 over b to the log base b of x. Okay, well, first and foremost, oops, what are you doing? So when I do this, b log base b of x is just 1 over x again. And so what we're going to see is this. That's a true statement. The derivative of any logarithm function, base b of x, is always going to be 1 over the ln of b times 1 over x. Okay? And that's how it's always going to come out to be when you play these games here. Now, your book writes it a little different. They just go, well, they put an a here sometimes, I think, on yours, if I'm not mistaken. They use the log base a. Another way they'll write this is they'll go 1 over x ln of b, which is the same thing. Okay, so that's in general for all logarithms. But wait a minute, what if it's the log base e? Well, the log base e is also known as the ln of x, right? But anyway, if you think about it, it actually follows the rule as well. It's 1 over x, right? It's 1 over x and then times the ln of the base, which is the ln of e. And the ln of e, of course, as we all know, is 1. Okay? So, I'm going to be doing some of those tonight. And then my favorite part of in 3.6 is spending some time doing some cool easy functions. So, for instance, you're going to find the log of this function here. Jiminy Christmas, that sure looks like it's what? This is a chain rule. It's a double chain rule because 3x is inside a square root and the square root's inside the natural log. So of course you could take the derivative of the natural log is just 1 over what's inside. Times, now what's the derivative of, remember that's 3x to the 1/2 power that you see right here, yes? What's the derivative of that? Y, of course, it's 1/2. 3x to the -1/2. Times the derivative of the inside, which of course is 3. So what I end up with here is this. This is 1 over square root of 3x. This is 1 over 2 square root of 3x times 3. And so that becomes 3 over, and that's going to be 2 times 3x, which is going to be 1 over 2x. And that's my answer. Now, interesting to note, we love logarithms. If you don't, you really should, because logarithms are awesome. This, you see, is exactly the same function, right? I just wrote it differently. Now remember, the power rule for logarithms says if you have an exponent up here, you can bring it out front and multiply it. So this is the same function as the one above. So if I take the derivative of this guy, I will get, well, again, I leave the half alone. I will get 1 over the inside, which is 3x, times the derivative of the inside, which is 3. The 3's cancel, and I get 1 over 2x. That little trick right here, rewriting stuff like this as this, and then bringing out front, will really make some problems a lot easier to mess with. For instance, this one here. Now at first you're like, why in the heck am I going to run into this problem? This problem really is illustrating how to use the tool correctly. Okay? Geez, it's a chain rule. Oh, it's a product. Oh, my lands. So remember, nice and easy, one byte at a time. So f prime of x is equal to, well, it's going to be 1 over all that inside mess. Don't touch it, just bring it, just bring it down. Times, now the derivative of that mess. Oh, geez, it's a product rule with chain rules. Hey, one piece at a time. So that's 2, 3x plus 1 to the first power times 3 times the second function plus the first times the derivative of the second function. Like so. Now when I do this and clean it up a little bit, I'm going to get 6. Good grief, I hate when it does that. 6, 3x plus 1s, 2x plus 1 sevenths, plus 2 and 4, 7 is 14. Over this mess. But what do they all have in common? Well, they all have one of those guys in common. So you could get rid of one of them. And they also have 6 of these dudes in common. So you can get rid of all 6 of those. It leaves you 1 here. Leaves you 1 here. So I end up with 6 times 2x plus 1 plus 14 times 3x plus 1 over 3x plus 1, 2x plus 1. And of course, you could FOIL that out and get 12x plus 12 plus 42x plus 14 over which of course is 54x plus 28 over 3x plus 1, 2x plus 1. Ta-da! That's a lot of work. Would you like to see an easier way, people? Because I think I would. Now, when you have this mess, what do we say it was? 3x plus 1 to the second, 2x plus 1 to the seventh. You recall back somewhere back in your past, your storied math career, that when you have the log of a product, that is equal to the sum of the logs. Right? Nice. But wait a minute. Where could this 2 and this 7 go? They could come out front. Whee! So 2 ln 3x plus 1. I'm just rewriting. Haven't done any differentiation yet. No big deal. Oh, that's nice. So this is still f of x. But what if I wanted to find f prime? Well, it'd be 2 times 1 over 3x plus 1 times the derivative of 3x plus 1, which is 3, plus 7 times 1 over 2x plus 1 times the derivative of the inside, which is 2. And you will end up with 6 over 3x plus 1 plus 7, or not 7, 14 rather, over 2x plus 1. And if you get a common denominator, you need to cross multiply. So you'd get 6 times 2x plus 1 plus 14, 3x plus 1 over 3x plus 1 times 2x plus 1. And it's the same answer we had a minute ago. Okay? That's a lot easier to work with. Now, we will use that when we get a function that looks something gross like the following. You will see, yeah, that one. Yeah, you could. Sure. Let's do x to the x power. That's just gross. I don't want to. I don't even know how to. So it's not x to the x times x to the x minus 1. It's not that, by the way. So I'd like to get this sucker down here where I can deal with it. Well, the only way I can do that is if I take the log of both sides. So watch me do it. So I get the ln of y equals the ln of x to the x power. Well, this fella can come out front. So it's the ln of y equals x ln of x. And then you're going, well, wait a minute. This looks like a job for implicit differentiation. So that's 1 over y, because the derivative of the natural log of y is 1 over y dy dx. And of course, this is a product rule, so the derivative of x is 1 ln of x plus x times the derivative of the natural log is just 1 over x. And so we end up with ln of x plus 1 over y dy dx. Now I need to solve for dy dx. So I'm going to get ln of x plus 1 x ln of I'm going to times it by y. But don't ever leave it like that because that's gross. So what's the ln of x plus 1? What is y? Well, y is this thing, is it not? So I'm just going to replace it with what y was initially, and I guess I erased it. Y was this thing here. So I just put it back in, and I'm done. Okay? Another one like that that's gross to work with. Oh, I don't know. Yeah, y equals square root of x. What does that even say? Well, I'm just going to call it x to the ln of x to the negative 2, I guess. Okay. Now remember, Now remember, this one actually can be cleaned up quite nice, because this is x to the negative 2. This is to the 1/2 power. So this is really just x to the minus 1, is it not? Okay. So that's kind of cool. But again, we haven't finished the derivative yet, so y prime would be equal to negative 1 x to the minus 2, right? Or negative 1 over x squared. Now, easy, didn't have to use log functions on that one, but I could have. I could very easily have done that. I could have left it like this and then take the natural log and brought the half down. It would have worked just as nicely. Maybe not as nicely as that one, because that one actually simplified wonderfully. But if you have, the fourth root, here we go. Y is the fourth root, that's disturbing, of x squared plus 1 over x minus 1, there you go, over x squared plus 1, like so. Well, this is gross, but of course it can be written as x squared minus 1 over x squared plus 1 to the 1/4 power. Ooh, there's a power. So I'll take the natural log of y is 1/4 natural log of this division rule. Okay, but there's more. If you recall, what happens when you divide inside of a logarithm? That is the same thing as doing what? Well, subtracting logarithms. So x squared minus 1 minus the ln of x squared plus 1. Like so, right? And of course, if you distribute that out, I'm going to, just to make my life a little easier. Let's take derivatives, shall we? So that's 1 over y dy dx equals 1/4, just stays here. The derivative of the natural log of this is 1 over that, times the inside derivative, which is 2x. And this is going to be 1/4, 1 over x squared plus 1, times the derivative of the inside, which is 2x. And so what I end up with is 1x over 2x squared minus 1s, I suppose, yes? Minus, again, that's x over 2x squared plus 1s. And I could take it a step further, get a common denominator, which means that this one would need an x squared plus 1. And this one would need an x squared minus 1. The bottom would just be this times this. And so I'd end up with x cubed plus x minus x cubed plus x over this. And the x cubes go away, and I end up with 2x, which is just going to be an x on top, and this business on the bottom then, because the 2 would cancel out, is equal to 1 over y dy dx. Well, I want to know what dy dx is, so what do? I multiply both sides by y. And what is y? Well, back in the original equation, we said y was this mess, right? Ta-da! And we're done. Now notice we could have done this one with the chain rule right off the bat. So I'm going to do it again with chain rule. I don't know that I like it, chain rule and a quotient rule. I'm not sure I like it as well as I do with log differentiation, but it's just another tool to have. So f prime is, well, it's 1/4 all of this garbage to the minus 3/4, right? Times the derivative of the inside, which would be what? Well, it would be 2x times the bottom minus 2x times the top over the bottom squared, right? Yes, it would. And so this would be 1/4. This is to the minus 3/4. I don't like that, so I'm going to flip it over if you don't mind and write that as x squared plus 1 over x squared minus 1 to the 3/4. If you FOIL this out, that's the same thing we had a minute ago. It's going to be 2 over, I think, right? 2 over, why does that look funny? 2 over x squared plus 1 squared. Right? Right. No, it's not. Hold up. I should not try to shortcut. Sorry. 2x cubed plus 2x minus 2x cubed plus 2x. So it's going to be 4x. Tried to take a shortcut in my head and screwed it up. Now, if you look at this, the 4's obviously cancel. Yes? That's nice. Look down here, though. This and this, these are all to the 3/4. But because the top and the bottom are to the 3/4, I could write them individually as to the 3/4 power. Are you with me on this? Okay. So what then I could do is, I could look at this in a couple of different ways. I think the easiest, maybe easiest way to look at it is, I could write that as x squared plus 1 cubed to the 1/4 power. You see that? And then it's x squared minus 1 to the 3 to the 1/4 power. Okay? Alright? And actually, well, let me back that up. I just thought of what I need to know. I know what I need to end up with is, I need to end up with this thing out here. You see that? But what is that? That is to the positive 1/4. And notice it's the opposite of what I have on the other page. On the other page, I've got this on the bottom. So I submit to you that this thing right here is equal to x squared plus 1, x squared minus 1 to the 1st power times the 4th root of x squared minus 1 over x squared plus 1. So in other words, that thing right there to the 3/4 is it to the 1st power times it to the, this would be to the minus 1/4 power here. You with me? So I'm going to introduce, I'm just going to come over here a little bit. So what I'm going to end up with is I'm going to rewrite this thing right here as this thing times this thing. So I'm going to have x squared plus 1 over x squared minus 1, like so, right, times x over x squared plus 1 squared times this mess. And I only know that because that's where I know where I need to go. But if I didn't know that ahead of time, what I'd end up with, I just end up with a different version of it. I probably, this is one of those deals where you go into the beauty parlor and you've got yourself a little picture what you want to look like. Make me look like Justin Bieber for some reason. And so they make your hair look like that. I know what I'm supposed to make it look like. This is what it's supposed to look like. That's the picture. And so because I know what it's supposed to look like, I can make it look like that. Oftentimes you really can't tell. I remember back in the day you try to describe to some old boy barber what you want to look like, and you know, they didn't pay any attention to you. They just did it however they thought looked good, and you're done. You're like, oh, not exactly what I wanted. So let's I think we do one more and then we call it a night. Okay. Ooh, doggy. So let's do y equal the sine of x to the ln of x. Nice. Listen, anytime you've got an x in the exponent, it's a dead giveaway. You probably ought to be doing log differentiation. I mean, that should be screaming. If it does not screaming to you, you turn your hearing aids back up, because it's screaming in my ears. Whenever I see this thing in an exponent, always take the log of both sides, right? Oops, then I didn't actually take the log of this side. Take the log of both sides, and then bring down the exponent, so it comes out front. So there's my exponent times the ln of the sine of x. And now, let's take derivatives. So 1 over y dy dx. Now this is a product. So the derivative of ln of x is 1 over x times the natural log of sine plus ln of x times 1 over the sine of x times the cosine of x, because that's the derivative of sine. So what I end up with 1 over x ln of sine of x plus ln of x times the, if you prefer, I guess you could write that as cotangent x, yes? Because cosine over sine. And then times the whole shoot and match by y. Well, what is the whole shoot and match? Well, I mean, what is y, rather, I should say? Well, it's right up above up there, sine of x. And that should be your answer right there. Okay? Again, if you're not seeing this right off, that's a big deal. You should be looking for that. Other times, you might have a function like the last one we had where it was some, it was x squared minus 1 over x squared plus 1 to the 1/4 power equals y. Hey, this is another one where it's nice to bring it down, because then I don't have to do chain rule. I could do it with log differentiation instead. But this one here doesn't scream log differentiation. It screams do it with chain rule. This one, however, to me, this one, wow, this one is just screeching in my ears. Because when I look at this problem, oops, not plus, you idiot. So when I look at this, I've got these nested beggars in there. That's a mess. I mean, yes, I can do it with product rule. Boy, I don't want to. I would much rather just do this, is rewrite this as the ln of 4x plus, I don't know what that's supposed to be, 4x plus 1, I guess, plus the ln of 2x minus 1 to the 7, plus the ln of x minus 2 to the 3rd power. And then it's just a piece of cake. 1 over y dy dx, again with the implicit differentiation. 7, ln of 4x plus 1. 7, oops, don't do this yet. I'm rewriting first. Now, 1 over y dy dx. That's 7 over 4x plus 1 times the derivative of that, which is 4. 7 over 2x minus 1 times the derivative of that, which is 2. 3 over x minus 2 times 1. So it's going to be 28 over 4x plus 1 plus 14 over 2x minus 1 plus 3 over x minus 2. All times y. Now what was y? Y is that mess up above. So 4x plus 1 to the 7th, 2x minus 1 to the 7th, x minus 2 to the 3rd. And for heaven's sakes, don't even try to multiply that out. I just don't think that's probably a very good idea. Well, it's not a bad idea, I guess. If you did it, what you'd end up with, you'd take this thing times this mess, and you'd get 28. One of the 4x plus 1s would cancel, so you'd get 4x plus 1 to the 6th, 2x minus 1 to the 7th, x minus 2 to the 3rd. And then the 14s, one of these guys would cancel off, and you get 14, 4x plus 1 to the 7, 2x minus 1 to the 6, x minus 2 cubed. and then 3, of course, and then 4x plus 1, 7, 2x minus 1, 7x minus 2 squared, and you're done. That's totally doable, and that's probably that's what you would have ended up with had you done it with the product rule. And so it'd look more like that just because that's how you came at it.